Now in lesson 2 of this particle model topic, we're looking at how objects or substances change the state of matter. So we know that a particular substance like water can either be solid as ice, liquid as liquid water, or a gas as water vapor. And that's the same as all other substances. They can exist in these different states. And we can change from one state to another, for example, from solid to liquid. And your first task is to label what these things are called when we change from one state to another. So once again, pause the video, check your answers. So from solid to liquid, that's called melting. Liquid to gas is called boiling. From liquid to solid, that's called freezing. And from gas to liquid, that's called condensing. And then there is another change that can happen from solid to gas, with something like solid carbon dioxide. That change of state is known as sublimating. So make sure you pause the video, check your answers, and then the next part of the task was you needed to fill in the missing words. So changes of states are physical changes. This means that a new substance is not created. Instead, we have a different form of the same substance. So it's important to realize that when there is a change in state, the particles themselves do not change. So if these are water particles, when it becomes a liquid, it's still water, it's still the same particles. To change the particles, there's a whole set of science just about how the particles themselves change whenever we create a new substance. And that science is called chemistry. And chemistry is in looking at chemical changes where we've had a chemical reaction. That is not the case here. These are only physical changes. There is no change to the particles, so the substance stays the same. Another thing about physical changes is that we can reverse a change in state. So we can, if we cause, say we've got some ice cubes and we put it in a warm room so the ice cubes then melt, we could put it back in the freezer and we get our ice cubes back again. So we can reverse a change in state in order to return the substance to its original form. Note, the substance itself hasn't been changed. It's still the same particles. It's just the state of matter that can change. During the state of matter, the number of particles does not change, merely the arrangement. Likewise, also the shape and the size of the particles also doesn't change. What this means is that there is no change in the mass. The mass is conserved in these state changes. Now, to understand how these changes in state happen, how we go from something where the particles are all in a regular arrangement to something where the particles are all moving around randomly in all directions and are very far apart. It's to do with the amount of energy that's stored by these particles that make up the substance. And we call this the internal energy. So the internal energy is the total energy that's stored by the particles that make up in the system. So the more that the particles vibrate or the more that they move, the more energy they have in their kinetic energy store. And remember, it's by changing the internal energy that allows us to change the state. So if we get the particles to move more or vibrate more, then we will increase the amount of energy in the kinetic energy store. They also have energy in their potential stores. Due to their positions. And you can think of this a little bit like springs. So with a spring, when we stretch the spring, we give it elastic potential energy. So likewise, especially in a solid where the forces have got a strong force of attraction between them, it's like that the particles are joined by a spring. And when we try and pull them apart, we're giving it a more elastic potential energy. So the total energy that the particles have in their kinetic and potential stores together that's called the internal energy. So it's all of the energy that the particles have together. So now when we heat a substance, if we got some ice, for example, and we heat a substance, what we're doing is we're transferring energy to the particles. And that will increase the energy in their kinetic energy store because they'll start to vibrate faster. If they're in the liquid form, they'll start to move faster. So whenever we transfer energy to particles by heating a substance, we're increasing their kinetic energy store. And this leads to an increase in temperature. Temperature is a measure of how quickly the particles are moving or how much energy there is in their kinetic energy store. So by putting in more heat energy, that gives the particles more kinetic energy, so they move faster. That leads to an increase in temperature because temperature is measuring how quickly they're moving. However, sometimes, as well as having an increase in energy, sometimes instead of having an increase in temperature, I should say, the increase in energy causes a change of state to go from solid to liquid or liquid to gas. So a change of state occurs if the substance is heated enough. The particles will have enough energy in their kinetic energy store to break the bonds holding them together. So if you imagine if the particles, and you can imagine they're held together by these strong forces of attraction like a spring holding them together. But if you were to cause the particles to vibrate more and more, eventually the bond will break and they will come apart. So to find out how much energy we need to change the state, we use something that we calculate, and that's called its specific latent heat, the amount of energy that we need to give something so that 1 kilogram of it will change state. Okay, once again, make sure you pause the video and check your answers. Now, there's a section here given over to boiling and evaporating, and this is important because these two words are often used interchangeably in everyday life. People might say evaporating, but they mean boiling, and they don't mean the same thing, and it's important to realize when you should use each of these words. So boiling, it only happens at the boiling point. Okay, so boiling happens at the boiling point. So for water, for example, that's 100 degrees. Okay, whereas evaporation can happen at any temperature. Why is that? Why is boiling only happening at the boiling point? Well, that's because boiling, for something to boil, it requires that all the particles have enough energy so the liquid can change to gas. So at the boiling point, all the particles are going to start moving apart, and it's going to change from being a liquid substance to being a gas. Now, evaporation, that can happen at any temperature, so that's different. So evaporation, why does evaporation happen? Well, evaporation is for single individual particles. So the thing to remember is boiling is about all the particles being able to change. They have enough energy so the substance can change from a liquid to a gas. Evaporation is just when an individual particle has enough energy to break the bonds and become a gas particle. Now that only happens at the surface of a material. Now, evaporation, boiling, we're putting heat in, the temperature doesn't change because all the heat is being used to give the particles enough energy so they can break all the bonds. But evaporation, that causes cooling, it causes the temperature to go down. Why? Because the most energetic particles leave the liquid. So the particles that are left have got less energy, and temperature is a measure of, on average, how much energy the particles have. So evaporation can happen at any temperature. It happens with individual particles, not with all of them. So evaporation is at any temperature, and it can happen with individual particles. It's only happening at the surface, and it causes cooling because these are energetic particles that are leaving, so the particles that are left over have less energy, so the temperature comes down. Boiling happens at the boiling point, so at a particular temperature, 100 degrees for water, and it requires that all particles have enough energy so that the substance can change to a gas. So make sure that you have paused the video and corrected your work. So we saw in the previous page that to find out how much energy we need to put in to change the state of something, because remember, to boil, for example, all the particles have to get enough energy for boiling to happen. And to find out how much energy we need to put in, we use something called the specific latent heat. And the specific latent heat, it's defined as the amount of energy needed to change 1 kilogram of a substance from one state to another without changing the temperature. So that's really important. You have to realize that when things are changing state, the temperature isn't changing. Even if we're continuing to heat the substance, we're continuing to put in heat energy, the temperature is not going to change. And the specific latent heat can be calculated from this equation. And this equation is given to you in your equation sheet in your exam, so you don't have to learn it. So the symbol for energy is E, and we show it as delta E. The delta means changing. So we're interested in the change in energy. How much energy we had to put in, how much extra energy is needed. So the change in energy is measured in joules, and joules can be shown capital J. The symbol for mass is, as usual, is little m, and it's measured in kilograms. And the symbol for specific latent heat is L, and that's measured in joules per kilogram. Now there are two types of specific latent heat that you need to know. When we're talking about the change of state between solid and liquid, so that's melting from solid to liquid or freezing from liquid to solid, we talk about the specific latent heat of fusion. If we're talking about the change from between liquid and gas state, then that's called the specific latent heat of vaporization. Now, there are two of these. Why are there two? Because for any substance, the amount of heat we need to put in, for example, to change from a solid to a liquid, from ice to liquid water, may not be the same as the amount of heat we need to put in to change from the liquid form, like liquid water, to the gas form, like water vapour. So you need to be careful that in a question, if they say the specific latent heat of fusion, they're talking about either melting or freezing, whereas if they talk about the latent specific heat of vaporization, they're talking about boiling or condensation. Okay, so given the equation above, your next task was to rearrange the equation for specific latent heat to make mass the subject. So we've got the change in energy is equal to mass times specific latent heat. We're multiplying by L, so to move this to the other side we need to divide both sides by L. So mass is equal to the change in energy, or the amount of energy we need to put in, divided by the specific latent heat. Mass is equal to the change in energy over specific latent heat. And then also you had to then rearrange the equation if we were calculating the specific latent heat. So here we need to divide both sides by m, so we've got the change in energy divided by the mass. L is equal to the change in energy divided by the mass. So make sure, once again, pause the video, check your answers, and make sure you've made any corrections or additions in green pen. Right, once more, some practice. We need to be sure that we have fully understood how we're able to use this equation, and as usual, the key thing is to use all 4 steps. So we've been asked to calculate the quantity of heat needed to convert 2 kilograms of water at 100 degrees into steam. So we're told that the mass is 2 kilograms. We're told at the top that the specific latent heat is 2,300,000 joules per kilogram, and we're looking for how much heat is needed. So the energy is equal to mass times specific latent heat. So that gives us the energy is equal to 2 times 2,300,000, which gives me an answer of the specific latent, the amount of energy needed to change 2 kilograms of water into steam is 4,600,000 joules. And the second question asked us to convert 3 kilograms of ice into water. So the mass is equal to 3 kilograms. In this case, it's assumed that the specific latent heat of fusion is the same, so we're going to say it's the same. In reality, it's not, but it's fine for this question. And again, we're looking for the energy. So we have the energy equals mass times specific latent heat, which gives us the energy is equal to 3 multiplied by 2,300,000, and that gives us that change in energy is 6,900,000 joules. And then finally we have calculate the mass of water converted into steam using this amount of energy. So we're looking for the mass. We have how much energy we've put in, 100,000 joules. We have a value for the specific latent heat. So again, we're going to use the equation. I'm going to rearrange it because mass is equal to change in energy over specific latent heat. So the mass is equal to 100,000 divided by 2,300,000. So putting that into my calculator. That gives me an answer of the mass is equal to 0.04 kilograms. Notice you could have 0.43 kilograms, would be fine. But notice I haven't used the recurring that appears whenever you do this calculation, and I don't write it in fraction form, always in a rounded decimal form. Right, so check your answers, make sure you've got all 4 steps for all of the questions. Now typically what we do in an experiment when we're looking to try and understand the changes of matter is we do an experiment where we have some material like ice, put it in a beaker, put a Bunsen burner underneath and start heating it to see what happens. And what we usually do is we'll record the temperature over time, how the temperature changes. So what we see is the temperature initially, as we expect, starts to go up as we're heating, but then it goes flat. That is, for some period of time, even though the Bunsen burner is still on, so it's still putting in heat energy, the temperature doesn't change. Then it's changed into liquid, so the liquid starts becoming hotter and hotter, the temperature's going up until it reaches 100, and here again the temperature doesn't change until all of the liquid has been changed into a gas, and then the gas will continue heating after that. Okay. So the thing you need to do is you need to label the graph, and you needed to make sure that all parts of the graph were shown. So we have labeled the graph to show which sections would require us to use specific latent heat and which sections would use specific heat capacity. Now, specific heat capacity is something that we met in the energy topic. So looking back through my pack, I go back all the way to lesson 1 on the specific heat capacity section of the energy topic, topic 1. And we find that specific heat capacity is the amount of energy we need to put in to raise the temperature of 1 kilogram of the substance. So once again, the thing to realize about specific heat capacity, it's about how much energy you need to change the temperature of a substance. Whereas when we're looking at the specific latent heat, we're looking at the amount of energy needed to change the state of a substance without changing the temperature. So specific heat capacity, we're changing the temperature. Specific latent heat, the temperature isn't changing. Okay. So, which parts of this graph show us where we're using a specific latent heat? So this is where the temperature is not changing. So we need to see where on the graph is the temperature not changing. Well, that's at this point, while it's boiling, the temperature isn't changing. We see that because the line is horizontal. And at this point, when it's melting, the line is horizontal, the temperature is not changing. So this is where we're using specific latent heat. Between the start and when it's 0 degrees, when it starts to melt, the temperature is changing. So this is to do with specific heat capacity. Once it's changed into a liquid at 0 up to 100, again the temperature is changing. So this is to do with specific heat capacity. And then finally, when it's boiled into a gas, it then starts to increase in temperature again. So this is to do with specific heat capacity. So if you ever have a question with one of these graphs and they're talking about the part of the graph where the line is horizontal, that's always to do with specific latent heat. Where the line is diagonal, that's to do with specific heat capacity. So the question that you've been asked is, why does temperature stay constant during this change of state? Okay, so the temperature remains constant even though heat is being added. So we're adding energy into the substance, but the temperature is not changing because the energy is used to break intermolecular bonds, to overcome those strong forces of attraction, not to increase the temperature. And likewise, when cooling, if the substance condenses, so changing from a gas to a liquid, or freezes, changing from a liquid to a solid, bonds are forming which release energy. Again, the temperature doesn't change. Right, now we had this question and we're looking at boiling a kettle and we're trying to understand what's involved in terms of how much energy we need to put in. So it tells us the kettle is rated at 3 kilowatts. So this is a measurement of power. So the first thing I notice, it's watts, so that means it's power. It's filled with 1 litre of water and it's at 10 degrees. I'm told the specific heat capacity of water and I'm told the specific latent heat of vaporization. And I'm told the density of water. How long will it take for the kettle to raise the temperature of water to the boiling point? So let's see what information we've been given. We've been told the specific heat capacity. Now here we are changing the temperature. And whenever you see the question where it's changing the temperature, that's to do with specific latent heat. So we're interested here in specific heat capacity, not specific latent heat. When we're changing the temperature, that's to do with specific heat capacity. So I'm told that the specific heat capacity is 4,200 joules per kilogram per degree. I'm also told that there's volume is 1 litre, and 1 litre is equal to 1,000 millilitres or 1,000 centimetres cubed, which is equal to 1,000th of a metre cubed. Okay, and we're told that the density is 1,000 kilograms per metre cubed. Now, this equation that we're going to find, will be given to you in your exam, but I'm going to look back through my notes all the way back to where we talked about specific heat capacity, and we were told that specific heat capacity, the energy that's needed is equal to the mass times the specific heat capacity times the change in temperature. Well, we're told that this change in temperature is equal to the end temperature minus the start. The end temperature is boiling point, so that's 100 degrees. The start temperature was 10 degrees, so that gives us a 90 degrees temperature change. Okay, now, have we got all the information we need? We've got C. We're looking for how long it's going to take for the kettle to raise the temperature. We've got C. We've got the change in temperature. Do we have M? Well, we've got the volume and we've got the density. So we can use the density equation to work out the mass. Remember, mass is equal to density times volume. So that's the first thing I'm going to do. I'm going to put in the numbers for that. So that's equal to 1,000 kilograms per meter cubed multiplied by our volume, which is 1,000th. So that gives me that the mass is 1 kilogram. And I can now put those numbers into here. So my energy that I need to be able to raise the temperature to boiling point is 1 multiplied by 4,200, specific heat capacity, multiplied by the change in temperature, which is 90, which gives me, I need to have 378,000 joules. Now, what I was looking for was not the energy, but the time. And I've also been given another number. I've been told that the power is equal to 3 kilowatts. That's equal to 3,000 watts. So I've got the energy and I've got the power, and I now need to work out the time, and I need to see how energy, power and time relate together. So the equation I can use is power is equal to energy divided by time, which gives me, rearranging this, that time is equal to energy divided by power. So I'm now substitute into this final equation. So I've got the time is equal to 378,000 divided by 3,000 to give an answer of time that will be taken is 126 seconds. Okay. So, a very difficult question. We're always using the 4 steps, writing out the numbers, writing out the equation, putting the numbers into the equation, calculating our answer. But here we needed to use the density equation to work out the mass, the specific heat capacity equation to work out how much energy was put in to cause the temperature to go up to the boiling point, and then finally the power and energy equation to work out how long that was going to take. Then it says, how long will it then take the kettle to change all the liquid water into steam? So again, we're going to use our power and energy equation. We still know the power, we're looking for the time, so we need to know how much energy it's going to take the kettle to change the liquid water into steam. So it's already reached 100 degrees. The temperature will no longer change, so there is no change in temperature as it changes state, which means that we are now going to use the specific latent heat. So what numbers do we know? Well, we know from the first part that the mass is equal to 1 kilograms. That hasn't changed. We know from the top here that the specific latent heat of vaporization is 2,260,000 joules per kilogram. And we're looking for the time, but in order to find the time, we're first going to find how much energy we've used. So the equation we've got is the amount of energy is equal to mass times specific latent heat. So that gives me the amount of energy is 1 multiplied by 2,260,000, which gives me the amount of energy needed to change all the liquid into steam, to boil all of the liquid, is 2,260,000 joules. I'm now going to use my equation power equals energy over time. Rearranged, time is equal to energy divided by power. And I can put now the numbers in. Well, I've got 2,260,000 joules, and I'm putting in 3 kilowatts, which is 3,000 watts, which gives me that, putting that into my calculator, the time is 753 seconds. Note, I have rounded my answer. I haven't put in any fractions and I haven't put in a recurring. So, a very difficult question, but by breaking it into parts and making sure we always clearly write out our numbers, write out the equations, we can manage to find the answers. And we have to remember that if we're talking about the temperature changing, we're using specific heat capacity. If we're talking about changing state with no temperature change, that's specific latent heat. So pause the video, make sure you've corrected your answers.